All right, let's talk about electric force quantitatively. And this is called Coulomb's law, after a physicist who first developed it in 1783. All right, now we know that like charges repel and that opposite charges attract. It's almost like the universe is trying to hide the fact that there's charge. If there's ever a big charge anywhere, like a big positive charge, it's going to attract all the negative charges to it and try to hide itself, shield itself away. And at the same time, all the positive charges are going to be pushed away. All right, well, we know that this positive charge and this negative charge are going to attract each other, but how much? Well, Coulomb's law says that the force of attraction or repulsion is given by a constant called the Coulomb's law constant times charge 1 times charge 2 divided by the distance between them squared. So it's an inverse square law case, just like gravity. In fact, it's exactly the same as gravity, except that this constant, this Coulomb's law constant, is huge in this case. 8.98 times 10 to the 9 Newton meters squared per Coulomb squared. The reason for that is that the Coulomb is an immensely large unit of charge. You will never see an entire Coulomb of charge anywhere because it'll just strip electrons and other charge off of neighboring atoms until it has shielded itself. All right, now one easy way to remember this number is to write it as approximately 9 times 10 to the 9. And then I always tell my students to just think of it as 9e9. 99. Easy enough. All right, let's do a couple of problems. We'll start off with some ones where we already know the force. So two charges feel an attractive force of 36 newtons. So now I want to know what the force will change to if I make the following modifications. First, I'm going to triple the distance between them. All right, so I'm not changing the charges, but I'm tripling the distance. Now, Coulomb's law says the distance appears squared and downstairs. So that means I've got 1 over tripling squared. 36 divided by 9 is 4. And therefore, the force becomes 4 newtons. All right, what if I double the distance and I triple one of the charges? Well, the charges appear upstairs, so the tripling is upstairs. The distance appears downstairs, but it's squared. So we'll have 2 squared. And then we'll have 36. 36 divided by 4 is 9. And 3 times 9 is 27. So there we go. See, it's real simple. We don't even need a calculator to do most of these problems. All right, what about if the distance and both of the charges are tripled? Well, in this case, each of the charges is upstairs. So I got triple, triple. Downstairs, I'm tripling the distance. So that's 3 squared. And then I got my 36. But here, all that business cancels. So that means if I do the same thing to both of the charges and to the distance, force is totally unchanged. So this is just 36 newtons. All right, second problem. Now in this one, we got to determine the force from Coulomb's law. What is the magnitude of the force between a 2 nanocoulomb charge and a negative 3 nanocoulomb charge that are separated by 3 millimeters? All right, one of the big things about electric charge is that the Coulomb is such a big unit. So you'll almost never see Coulomb by itself. It almost always comes with prefixes like micro and nano. Remember that micro is 10 to the minus 6 and nano is 10 to the minus 9. So let's go ahead and calculate this force. Force K Q1 Q2 R squared. All right, plug in. 9 times 10 to the 9. Now I got to use SI units. So our first charge is 2 nanocoulombs. So we got 2 times 10 to the minus 9. Second charge is negative 3 nanocoulombs. And the distance is 3 millimeters. Again, I've got to make that in SI. Now, this always happens, or almost always happens, when we're doing electrostatic problems and also in gravity problems. We've got bunches of numbers and bunches of tens all multiplied and divided. The easiest way to do this is to do all the numbers first and then do all the tens. So I'll write this as 9 2, negative 3, 3 squared. So I just did the numbers, and now we'll do the tens. 9 minus 9. Oh, this should be minus 9. Look at that. Minus 9, right? And then it's negative 3 squared. So these two, because this is in the exponent, I'm going to multiply. So it'll be negative 6. But it's downstairs. So really, it's plus 6. And then we'll have 9 cancels. 2 times negative 3 is negative 6. 9 minus 9 is 0. Minus 9 plus 6, that's negative 3. What's my unit? Well, it's SI, and it's a force, so got to be newtons. So I'll write the magnitude as 6 millinewtons. Notice I dropped the minus sign, because all the minus sign is telling me is that it's attractive. All right, that's Coulomb's law.